14.4, differentials and linearization. When you took Calculus 1, you saw a differential formula, and it said df dx is equal to f prime of x, and you multiply by df dx, you have f prime of x dx, and this was called the differential of f. And we took that as an approximation formula. Delta f is approximately equal to f prime of x delta x. This is, in reality, this is a limit formula. This is as delta x and delta f approach 0, this became approximately true. And of course, you can use this to generate this approximation formula. In a multivariable situation, we actually have two ways in which f can be changed. F can be changed by changing x and changing y, and so we have two terms. This gives us total differential. I'm going to write that over here. Total differential. So for instance, if f of xy is equal to x squared plus 2y squared, df would be, partial of f with respect to x would be 2x dx, and partial of f with respect to y would be 4y dy. If you just change x, then we have this term that agrees with what we had in Calculus 1, but if you change both, you have to have two terms. Both terms, both changes, both dx and dy, will affect the change in f, and this adds up to give you the change. So now, given this differential, let's suppose xy changes from 2, 3 to 2.1, 3.1. What happens to f? This is a pretty important question. If we change these independent variables, how does f change? Okay. This could be some real physical quantity, for instance. This could be a position in space. This could be a force as a function of position. How does the force change? Pretty important. That changes the acceleration of a body acting under that force. So this could be what we're getting at in a real physical situation. Okay. A, find delta f. Okay. Well, first of all, you can calculate f of 2, 3. And that ends up being 2 squared plus 2 times 3 squared. And that's 9 times 2, 18, and 4 is 22. And you can calculate f of 2.1, 3.1. 2.1 squared plus 2 times 3.1 squared. 2.1 squared is 4.41. And 3.1 squared, 3.1, 3.1, I believe that's 9.61. If you multiply all those four terms and add them together, and that's 9.3, and 0.3 is 0.6, and then 0.1 is 0.01, which you can certainly do for 2.1. It gives you 4, and then 0.2 and 0.2 is 0.4, and then the 0.01. Now, if you add that up, you get 4.41 plus 19.22, I believe that is. 2 times 9.6 is 19.2, and 2 times that sounds about right. And we get 23.63. Okay, see these two values? You can tell what happened. We change x by a tenth, we change y by a tenth, what happens? The function changes by 1.63. Let me write that down officially. This has nothing to do with calculus. This is just plugging in just simple algebra. Delta f is going to be f of 2.1, 3.1 minus f of 2, 3. It's just final minus initial, that's all. 23.63 minus 22, 1.63. Okay, keep that in mind. Now let's use differentials. This would be an exact change. We have this curvy surface and we're moving from one horizontal location to another. What happened on the surface? We changed our elevation changed by 1.63 units. We can approximate this. Delta F will approximate delta F, or delta F will be approximated by dF, whichever way you want to state it. We have our total differential. dF is equal to 2x dx plus 4y dy. Now we're going to start at 2, 3, and I'm going to let dx be 2.1 minus 2, which is 0.1. dy is 3.1 minus 3, which is 0.1. And then we can substitute, we get df, which is equal to 2 times 0.1, plus 4 times 3 times 0.1. 0.4, 1.2, we get 1.6. Okay, how does that compare to that? Well, it's very close. This gives you an approximation. This gives you an exact value. So what's happening dimensionally speaking, geometrically speaking, is you may recognize this is an elliptic paraboloid. Looks like this, and we're at some point on here. This differential actually gives you a tangent plane approximation. That's what the differential of df gives you. And given the concavity of this, if you put a tangent plane on this, it makes sense that this is less than that. This follows the curvature of the surface, and this continues off on the tangent plane. If we were to increase dx and dy, these would diverge from each other. If, for instance, if you change x by 5 and change y by 5, you'd find that you wouldn't see any relationship between these two. This surface follows a curved path. This tangent plane goes off like that. So now, you may ask why use this sort of linearization when we have the real thing? Well, we can solve some interesting problems. Let me give you an example. Very simple formula. Volume is equal to pi r squared h. It's the volume of the cylinder. That's the radius. That's the height. Pi r squared, area of the base. H is the height. We can calculate the total differential. Partial of v with respect to r is 2 pi rh dr. Partial with respect to h is just pi r squared dH. And this gives us a way of relating a change in R and a change in H to the change in the volume. So let's suppose we measure R and H, and these are off by plus 2% each. Okay, and who knows why? This could be an oil tank, and we could be using an indirect method of measuring it, some sort of triangulation or whatever. And maybe we're measuring from the outside, we're not sure exactly how thick the base is, but whatever, we know that the height is accurate to within 2%. Same thing for the radius. Maybe you can't get inside it, we measure the outer radius, and use that to infer we measure the outer circumference, use that to infer what the radius is. And maybe we can't get all the way around, we have to estimate it or something, but we're certain that we're off by we're within 2%. So this would be maximum, I suppose you could say. We're off by a maximum plus or minus 2%. How accurate is our volume? Well, we could ask if we're off by 2%, how much will the volume change by? And that would give us a maximum volume. It'd be pretty good to know, especially if we're storing something in here that's of critical importance. Well, here's how we're going to do it. We don't know the radius and the height. We don't even care about what the radius and the height is, but this 2% is pretty important. We know that dr over r, I'm going to make that 0.02, and dH over h is 0.02. This is like a relative error. You study this sort of thing in chemistry. It's the change in radius over the radius is 2%. The change in height over the height is 2%. Well, this tells us also that dr is 0.02 r, and tells us that dH is 0.02 h. So we can substitute, we get dV is equal to 2 pi r h. For dr, we're going to put 0.02 r, and then we have plus pi r squared, dH 0.02 h. And then what we can do is multiply 0.02 times 2 is 0.04 pi r squared h, plus 0.02 pi r squared h, and we get 0.06 pi r squared h. Well, we have dV equals. Now, if we want to put this into some sort of usable format, I can divide that side by v, and I can divide this side by the algebraic equivalent of v, pi r squared h. That cancels, and we get dv over v is 0.06. Okay, v changes by at most 6%. Okay, and that's where we can use differentials. So that's part 2. We'll be back with part 3. We're going to talk about linearization. That's for the next video.